Hi, everybody. We're going to take another look at the history of the Earth and how do we know how old it is? We've already talked about this a little bit, but we know that the Earth is about 4.5 billion years old, and we can do that through radiometric dating of rocks. Um, but we also can look at things around us and look at and realize that we're not that young. I mean, you look at you just watched a video on Hadrian's Wall, and it goes from here to here. It literally cuts across Great Britain. And in 1802, a geologist named William Hutton walked the length of Hadrian's Wall, and he noticed that it was the same granite as these mountains behind it. And he knew that this wall was, at least 1,000 years old at that point already, because it was, constructed in 122 AD. And it was still in good shape, but the mountains that the granites came from, they'd all worn down into these nubs. I mean, it's the same stuff. So if this has been standing for over 1,000 years by 1800, and it hasn't really shown any weathering, then these mountains that the rocks came from must be extraordinarily old, into the tens of thousands, to have that much erosion take place. In fact, we know that that range formed about 50,000 years ago. So everyone, up until we had more definitive proof, really struggled to understand how things worked. And Everest was such a weird thing because way up here in these really tall layers up into the atmosphere, you can find ammonite fossils. And ammonite fossils are only found in the sea. So ancient peoples thought, well, if you have sea fossils there, at some point, you must have had a massive flood. Well, that's really not what happened. What happened was we had tectonic movements. We had the Indian Australian plate literally ramming into the Eurasian plate. We had subduction zone here and some basically crinkling, like take a piece of paper and crumple it up, and you're going to get kind of the same folding here. And these folds are the Himalayas. So really, these shells weren't deposited way up here. They were deposited down on the ocean floor, and that floor got pushed up. And so that had to have taken lots and lots of time, and we have to have a mechanism for that. Remember, that's our plate tectonics. So we know that Earth has an immense age. And we also know that at the mid-Atlantic ridge, we start to split apart. Remember, our fingernails are about the rate at which that splits apart every year. We're not getting that much farther away from Europe in our lifetime. I mean, you're talking yards. You're not talking miles. But if you put it into the context of geologic time over millions of years, we can have things moving. And if you go into the Antarctic, which has really, except on the fringes of the ocean where some things come up onto land, it is so cold that really there's nothing growing there. You wouldn't expect to find fossils, but we do. In fact, it's a marvelous bed of fossils. But the thing is, you find this thing like this polar allosaur, and that's a warm-blooded creature. If it gets too cold, it just doesn't function. It's a cold-blooded creature. It needs heat. Well, the Antarctic isn't right now a hot zone. It's not a tropical place. It's cold. We get some melting, but we still have more, glaciers developing there. But we have fossil evidence that says there were warm-blooded creatures there. And remember, if we go back to that Pangea thing and we look at the Glossopteris fern, Alfred Wegener figured out the shape of the continents, and there's some mountain belts that kind of line up if you line them up. But remember, if we go to the continental plate, these really line up well. And then he found all this fossil evidence. So you've got the Mesosaur in South Africa and South America, and they were there. The fossils show that they're there at the same time. But the thing is, this is a land creature. It could not have crossed that vast ocean. And we have this Glossopteris fern that we can find the same fossils from the same time period through Australia, Antarctica, India, Madagascar, into Africa, and all the way to South America. This is a tropical plant. Last time I checked, this is not a tropical continent anymore, but at one time it was. And there's also some glacier striations, if you remember that from last year, that really show there's a lot of evidence. But it wasn't until HIST came along during World War II and left his sonar on as he came back and forth from Great Britain to deliver goods to keep the war efforts going. And he found the Mid-Atlantic Ridge. He found then, as they came back later after the war to do research, that we were actually getting older on either side of the ridge at the same time span. So they mirror each other. So he found the mechanism for allowing this to push apart, which then allows for the subduction to happen on the other side, because our planet's not getting bigger. So where it's created on one part, it's destroyed on the other, and we get something like mountain ranges. Remembering back to last year, the law of superposition says that the farther down we go, the older it should be. So we can do relative dating and we can do absolute dating. And we can also tell, as we look through the fossil record, as we go farther back in time, life gets less complex. I mean, you can get back to a point where you're not really seeing eyes, or you're not really seeing, go far enough back, we're not seeing backbones. You can see that progression as life gets more and more complex, the higher towards the surface we go. The less complex, the farther down we go. That's that law of superposition. And law of superposition allows us even to look at layers of rock. So we'd say, just by looking at it, that on the bottom, this should be the oldest, and the number 4, the limestone, should be the youngest, right? Because it's on the top. But if we look at this, we can have an intrusion, which is really just magma coming up and kind of melting it and forcing its way up. And look, it actually cut across the shale and the sandstone. And we can date this back through radiometric dating to know that this granite hardened about 85 million years ago. But this lava flow cooled 80 million years ago. So guess what? This shale has to have been deposited sometime between those two times. So we know that this intrusion is younger than these two layers, but guess what? It's older than this one because this one cuts across the top. So law of superposition can tell us a lot about the relative age of things. Just by looking at it, we can tell what should be older and what should be younger. But if we want that absolute dating, well, then we've got to get into some going past the relative dating. Remember, the farther down we go, the older it should be, into some absolute dating. Now, the cool thing about absolute dating, if we can find out what age this rock is, and we find a trilobite, it's called an index fossil, it tells us anywhere we find that specific fossil, anywhere in the world, it should be about this age. And index fossils have to be abundant and live for a relatively short period of time so that we're able to date them. So if you find a trilobite, you're going to find it at this age, which we know has to be older than this one because it's up higher. If you find the ammonite shell, it's much younger than the trilobite. If you find the gastropod, it's somewhere in between, because look, the gastropod actually covers 4 layers. So it's younger than the trilobite, and it could be younger than the ammonite. But in some places, we have both of those fossils in the same place. So if we get into absolute dating, so let's get into that uranium. Uranium breaks down into lead. And when magma cools deep in the earth, it actually has some uranium. It has different things that cool into the crystals. And it slowly decays over time. And there's this thing called half-life that we've already talked about. And remember, in half-life, we start out with 100% uranium. After one half-life, half of the uranium's gone. After 2 half-lives, half of what was left is gone. So 50% is here. At a second half-life, it's half of the 50. So now we're down to 25. And after 25, it would go to 12 and a half. So that means that at this point, at this first half-life, which is just in this case, it's saying millions of years. So we're really getting into, in fact, it's saying this half-life is 704 million years. It would take that long for half of the uranium to turn into lead-207. So a half-life is how many years it takes for half of the parent substance to turn into the daughter product. And so in this case, the parent product is uranium, the daughter product is lead. You can also do this with carbon-14. It's got a much younger half-life. It's only around 5,000 some years old. I wouldn't make you know that exact date, but I may make you look on a graph to figure it out. And so you can see, if we go to 50%, here's my first half-life. Half of 50% is 25. So I find that. Here's my second half-life. Half of 25 is 12 and a half. So it's right above there. Here's my third half-life. Half of 12 and a half is 6.25. So around here. So by here, we've had 4 half-lives. That means at this point, there's only 12.5% that's the original amount of carbon-14. And The rest of it, that 87.5%, has now decayed into the daughter product. So if we have something that you find in the ground, like a bird that might have just passed away, which is always sad, it would have a lot more carbon-14 in it than, say, this mummy that's been dead for hundreds or 1,000 years or more. And this is going to have a lot less carbon-14 in it, therefore allowing us to date. Now, this actually would probably be a little too new dead to date, but it's just, this would be 100% just starting to decay. So let's take a look and see how some decay rates go. We're looking at, let me try that again. Okay, let's try that again. We're looking at decay rates. We can actually look at the half-life. And in this case, we're doing carbon-14 and it changes into nitrogen-14. So let's put all the nucleus out and see what happens. And you see it's starting to change. These decay from carbon into nitrogen. And it continues until it gets as close to zero as you can get. Okay, that video is there if you need to go back and look at that. Obviously, we just talked about it, so I'm not going to go through the old thing. But this one is interesting. This is really showing you that combination of absolute dating, so using a device to figure out how much of the radioactive substance is left into it, versus relative dating, basically saying this is much newer dead than the stuff down here, and this is older yet. This is looking at kind of a combination of relative dating and absolute dating. As you can see, I've already taken my microphone and used carbon, and it's not a microphone on wood, but I used uranium on the rock, and on the newly only 154-year-old skull, I used carbon-14. So what we did is we went here, and as we placed this, and I realized you can't use uranium, I would just go and find how much had gone, and it says it's 98.2% of the uranium or carbon-14, is left, which tells me it's 154 years old. But again, to do a rock, I had to switch over to uranium-220, and that's still, remember, uranium's half-life is over 4 billion years, and I'm at 97.9%, which means if I get all the way over there, it's about 142 million years old. Okay, so we go on and talk more about that. And again, if you want to take a look at that, it's in the notes that I left for you. So let's take a look at this video.
The Earth has been trying to hide its age for millennia, but now we know, thanks to science. Elise, how old are you?
You'll have to count my atoms to find out.
Hey y'all, Trace here for D News with our friend Elise Andrew from I Love Science. Hey Elise.
Hi Trace, hi everyone out there. I'm sure you've heard by now the oldest rock in the world was discovered on a sheep ranch in Western Australia, and the findings were published in the journal Nature Geoscience over the weekend. The gem comes from the crust of the early Earth and has been dated to an astonishing 4.4 billion years old.
We actually just did a video about carbon dating, but that is totally child's play in comparison to this. Carbon dating can only look back about 40,000 years, give or take a few thousand, about 8 half-lives of carbon. But this rock was dated 10 years ago, and this new paper confirms and revises the previous one. So science sometimes takes a little long, guys.
In this case, the researcher used a dating method called uranium-lead dating. It's similar to radiocarbon dating, but they're measuring using the half-lives of uranium atoms instead. For example, uranium-238 or 235 will decay into lead given enough time. Depending on the uranium isotope, the half-life can be as high as 4.47 billion years. With huge numbers like that, we can effectively date rocks even older than the Earth itself.
That is pretty cool. When a gem called zircon cools, the crystalline structure is locked. Thus, the amount of radioactive uranium is fixed. As decay occurs, high-energy particles emitted from the uranium might be knocking the other atoms of lead out of that gem. If any of those atoms are leaking out, the whole uranium-lead process is screwed.
Which is precisely why this zircon took so long to date. Scientists wanted to confirm without a doubt the uranium-lead dating was accurate, and this paper is the definitive study. They literally counted every single lead atom in this gem using something called atom probe tomography.
I can't believe that.
Every single one.
That's crazy. The atom tomography uses ion beams to measure where every single atom is inside of a substance. It has to be done in a vacuum chamber at temperatures approaching absolute zero, so that way the atoms don't move too much. We're talking like, atoms are they're real crazy tiny. So even a little bit of movement, the whole thing is ruined. And again, like I said, science takes a little while.
Regardless, once we've measured the amount of lead, the actual math was easy. Zircon is 4.374 billion years old. Done.
Easy peasy. Looking at the little atoms of this zircon can teach us a lot about the formation of our planet and its makeup at the time the rock was formed. Trace elements in the zircon tell us the planet was wet, which means it cooled pretty quickly after a collision ripped off a chunk and created the moon. And that's like a whole other story. We won't get into it.
All of this means that there was solid rock and liquid water on Earth just 165 million years after the solar system formed. Before this one was found, Quebec had the record for the oldest rock. It was dated in 2008 at 4.28 billion years old.
So make sure you subscribe and tell us what you think down in the comments down there. Thanks for coming.
Okay, so we can take both of these again. We talked about this a second ago. Take absolute and relative dating and combine them, because we can also look at things called, sometimes we have trouble dating this rock. We know that roughly this, fossilized shell should be about this old, but there's oftentimes layers of ash. When volcanoes explode, they actually can put a layer of ash down all over the world. And if we find this same layer of ash, we can actually radiometrically date the ash. So we know that this ash layer is 495 million years old, where this layer is 510 million years old. So then we know that basically in between these two, any of these things, this should be closer to the 510 million, this should be closer to the 495 million, and this fossil needs to be somewhere in that date range. And we can do that with all the different layers of ash, which is a really helpful thing for us to use.
Hi, I'm Mark Schmitz. I'm a geologist, and I'm here at John Day Fossil Beds National Monument in Oregon, again studying the history of John Day fossil beds by looking at the different rocks exposed in these outcrops. Here we have a very interesting outcrop which allows us to look at two different ways of dating rocks. Using superposition, one of the principles of relative dating, we can determine that the relative ages of this green siltstone versus this very interesting rock above it. This rock is a volcanic ash. The green siltstone, because it is lying below the volcanic ash, is older. Older siltstone with an overlying volcanic ash, which is younger. We have the opportunity here, because this is a volcanic ash, to actually complement relative dating with an absolute radiometric date. We can assign a number in millions of years to this volcanic rock. The volcanic ash contains minerals like zircon, feldspar, and biotite, which contain natural amounts of radioactive elements like uranium and potassium. Those radioactive elements then decay to their daughter products, lead and argon. It is that decay that provides us with our natural clock for determining the absolute age of this volcanic ash.
Okay, so we can use carbon dating for things that are like 5,000 years and younger, and a little older. We can use uranium dating, but we also have other things that tell us kind of not just how old the Earth is, but tell us the conditions that were on the Earth. And we can use things like tree rings and ice cores and varves. And you don't know what a varve is, but you will by the end of this video. And if you do, good for you. A tree ring, well, you guys know this. You can count the tree rings. You guys have probably had to count that in there. And if you look at this, you're like, hey, wait, that year 8, if I made that picture bigger, that's an 8. That was a pretty good growth year compared to this set coming here, 9, 10, 11, doesn't look so great. Year 2 looks like a good growth year, because the light bands are the summer growth, and the dark bands, there is a little growth that happens in winter, but it's not very much, and it's much slower. And so we can count the bands. Now, the interesting thing is, as you look at it, it can also tell us during the lifetime of this tree, which is about in 1913. If we look at this part here, if we count back, we know that's when it sprouted, because that's 113 rings ago. But we also can tell you that there was a fast growth in 1918, so it was a good year. But if we go all the way down here, right here, in 1939, if we follow this in, there's a charcoal layer. And so there was a fire year. And so we know we had a fire in 1939. In 1951, we had a really dry period. Look how much smaller those rings are. And in 1966, right here, there's an insect infestation. So we can tell a lot about our climate. What conditions have to be there to have an insect infestation? What conditions would there have to be to have a tendency for fire? When are you having good growth? And if you go down like into Louisiana where you have hurricanes, what happens is we can actually tell really big hurricane years, because what happens is you get this surge of water coming in, so it brings some salt water in to flood the area, and the salt water actually reacts with the tree and it forms actual blue layers, and that's that salt being inundated, and you get a blue color ring. And so we know that there had to have been a hurricane in 1823 and 1878 and 1950, because we can count the rings back on a live tree, and when we find the blue ones, we know there had to have been a significant enough hurricane to flood that particular area. And then we can go back in farther with petrified wood. The oldest piece of petrified wood we found, which was actually a fern, not a tree as you'd expect, almost 400 million years old, 390 million years ago. And with that, we can tell the same thing in the petrified wood, because we can still see when were good growth years, when weren't. So this is a quick video on telling us what trees can tell us. 2 minutes.
You might call him Lord of the Rings.
The tree ring lab is hands-on, and so we encourage everybody to touch these pieces of wood. This is a cross-section of a redwood tree.
David Staley is a dendrochronologist at the University of Arkansas.
The annual growth rings in trees are a natural archive of environmental history. The time series history of fat rings and skinny rings is telling you about the history of wet years and dry years. So this is a piece of African bloodwood. This was found in western Zimbabwe.
Long before high-tech weather instruments, nature has kept precise records of rain, drought, even fires.
The climate history encoded in the annual rings of trees is unique. It's like fingerprinting.
Staley is helping Mexico prepare for future droughts by looking at how trees responded to severe drought in the past. That will help fine-tune predictions about how future dry spells will impact the ecosystem and could help the country prepare for future water and energy needs.
One notion is that this 21st century drought may be being aggravated by human activity, both at the global scale and at the regional scale due to land surface changes.
Deciphering tree rings can also help historians solve mysteries, like the fate of the New World's lost colony of Roanoke. Could drought have been a factor?
This is a piece of bald cypress from Blackwater River, Virginia. That is the most severe drought of 800 years in this part of the United States. And that's a significant year because of the disappearance of Virginia Dare and the other colonists at the Roanoke colony in North Carolina. It's a Swedish increment borer, and with this tool we can extract the core sample without seriously harming the tree.
In the field, Staley and his team target old-growth forests with the least imprint of human activity.
Oh man, these are stupendous trees. They're so precious.
And that's a ringing endorsement from this Lord of the Rings. For Science Nation, I'm Miles O'Brien.
Okay, so now let's get into some ice cores. Ice cores are interesting because as old as we can get with the ice, we can not only see how much was deposited. Now remember, to get a glacier, to get one of these things, you have to have more snow than ablation. In other words, more snow than melts the next summer. And you actually get dark and light bands. Light bands are during the summer, during the melt, and the dark bands are the thicker snow building up, and it melts back down. And you can literally count back the layers. Now the interesting thing, you can literally see the layering. Here's the light bands of summer where it melts, and then the dark bands of buildup. And it gets compressed over ages. And in the Antarctic, we can get, in Greenland, really good ice core data back to about 400,000 years. And the cool thing about that is trapped in those layers are little gas bubbles. And in that, it tells us what our atmosphere was like. In fact, there's one place now in Antarctica that we think we've found an ice core back to the last 1,000,000 years. And so that's going to be really exciting to see some of that data come out. This is crazy. This is Antarctic ice, and this is U.S. pollution. In the 1970s, we passed the Clean Air Act, and this is that 1970 something mark, which delineates when we stopped half of our pollution going in and it stopped getting deposited. All of this is the Industrial Revolution leading up to the 50s, where we were putting a ton out. And this is where the U.S. put the clean air. Now, can you imagine the whole world if we did that? How much better our ice core is? We have residue from chemicals from plants in Minnesota that we can find in human bodies all over the world, but we can also find it in Antarctic ice. Remember, we might have different countries, but our weather patterns, our air travels all over the globe. And ice cores can tell us so much by what's trapped inside.
This frozen library, the National Ice Core Lab in Denver, Colorado, has ice from all over, kept at minus 35 degrees.
It's cold.
The oldest core here goes back some 400,000 years. Here, really ancient ice from Greenland in the north and Antarctica in the south reveals Earth's climate history. Let's see what cores like this can tell us. First are those layers I mentioned in the New Zealand snow. They've turned to ice, and we can count them. Summer, winter, like tree rings. We can date the core.
And they never touch it with their bare hands.
Other cores tell other stories. Look at this. It's the ash of an Icelandic volcano that blew up to Greenland 50,000 years ago. Cores hold other and even more important secrets. Look at these bubbles. They formed as the snow turned to ice and trapped old air that's still in there. Scientists now are working with cores from Antarctica that go back even further. They tell us with a very high degree of accuracy how much carbon dioxide was in the air that far back. Researchers break chunks of ice in vacuum chambers and carefully analyze the gases that come off.
You know, even with their gloves, they have flat plastic on top.
Levels of carbon dioxide in that ancient air. Looking at the cores, we see a pattern that repeats. 280 parts per million of CO2, then 180, 280, 180, 280. By analyzing the chemistry of the oxygen atoms in the ice, you can also see the pattern of rising and falling temperature over time. Colder during the ice ages, warmer during the interglacial periods. Now put the two lines together, and you can see how closely temperature and carbon dioxide track each other. They're not exactly alike. At times, the orbits caused a little temperature change before the feedback effects of CO2 joined in. But just as we saw in New Zealand, we can't explain the large size of the changes in temperature without the effects of CO2. This is the signature of natural variation. The cycle of the ice age is driven by changes in Earth's orbit with no human involvement. But here's where we are today. In just 250 years since the Industrial Revolution, we've blown past 380 with no sign of slowing down. It's a level not seen in more than 400,000 years, 40 times longer than the oldest human civilization.
Okay, so that's an important thing to understand, that we know that we get warmer and colder, and that is that whole handy-dandy wobble of the Earth and changing our orbital distance, and that does affect our climate. But it's a nice repeating pattern, and ice cores show us that. This is what we're happening right now. This is Industrial Revolution to today. In fact, it's not even Industrial Revolution. This is in the last 20 years. You're going to have obviously some questions throughout here, but there's one last thing we really need to look at, and those are varves. And the cool thing about varves, they're like glaciers and tree rings. They get layered in every year, and we can count the layers. But these layers are made of mud. and clay that form near lakes and rivers and glaciers and oceans. So we can find varves in a lot of different places. And just like tree rings and ice cores, the light areas are the summer and the dark areas are the winter deposits, because you have different amounts of sediment. Like if you're in Lake Superior, you're going to have a much different drainage coming in the winter with ice covering. It's going to really slow the deposition, versus in the summer when you have things washing off of the shore into the lake. The same thing with the oceans, or when the melting glaciers occur. And again, it traps in little particles of gases. So we can actually look at ancient atmospheres through varves, through this mud. And as old as you can get mud, as far that hasn't been touched, we can go back in history. So mud's been around for billions of years. So we can have, if we get the right spot, we can get hundreds of millions of years worth of data through a varve. And so ice cores can tell us back up to 1 million years. Tree rings, depending on if they're petrified or not, really good evidence for the last up to 500-600 years. And really the muds give us the whole spiel as far back as we can go. And those are some of the things how we know how old things are. We also know the composition of the atmosphere, and we're going to be taking a lot more in-depth look of that atmosphere in our next unit.